morning, students. Today is the 22nd session and the second class in crystal field theory. Today we are going to study about the octahedral symmetry. So in crystal field theory, in today's class we are going to study regarding the octahedral symmetry. Actually, what are we going to study in octahedral symmetry? So first let us see the shape of an octahedron. In the crystal field theory, we are going to observe a central metal atom, and this is going to be surrounded by the ligands. That is, it will be having 6 ligands. It is going to have 6 ligands and in a regular tetrahedron. Now, what are we going to study in this octahedral symmetries? Like when the ligands are going to approach, how the degenerate d orbitals are undergoing a splitting of the orbitals. So, what are we going to observe in octahedral symmetry in coordination chemistry, that is in crystal field theory? In octahedral symmetry, the d orbitals are going to split up into a sets with energy difference. That is, in octahedral symmetry, the d orbitals are going to split into 2 sets with an energy difference. And this energy difference is denoted as delta oct. This is going to be denoted as delta oct. So, here what do we observe in octahedral symmetry is going to be the d orbitals are going to split with an energy difference of delta oct. And the crystal field splitting parameter is commonly denoted. The splitting parameter is commonly denoted by 10 dq. And what does a 10 dq mean? 10 dq actually means 10 times of differential quantum. So this difference between the two energy series is going to be 10 dq, and this is called as 10 times of differential quantum. They are going to get split up into 2 sets, and one of the set is going to be dxy, dxz, dyz. These 3 orbitals will have lower in energy. dxy, dxz and dyz orbitals will have lower in energy, and they are collectively referred to as T2g. So the 3 d orbitals which are going to split, and these will have a lower energy, and they are called as T2g, and this happens in octahedral symmetry. So dxy, dxz and dyz, there is going to be a lowering of energy, and these 3 d orbitals are called as T2g. Next is dz square and dx square minus y square will have a higher energy. dz square and dx square minus y square will have a higher energy, and they are referred as Eg. So the 2 orbitals dz square and dx square minus y square which have higher energy are referred as Ez, while the 3 orbitals which have lower energy dxy, dxz and dyz will be referred as T2g. The reason for the difference in energy is because the former group, that is dxy, dxz and dyz, are going to have a repulsions. They are going to experience a greater repulsions. So they are going to have a higher energy. They are going to experience a lower repulsions. Because they experience a lower repulsions, they are going to have a lower energy. While the dz square, dx square minus y square will have a higher repulsion. Because they experience a higher repulsion, they are going to have a greater energy. So the reason for the difference in energy is because the former group is farther from the ligand. They are far away from the ligand and then the later, and therefore they are going to experience a less repulsion. So these are the 5d orbitals. These are the 5d orbitals when the ligands are going to approach. When the ligands are going to approach in an octahedral field. Remember the 5d orbitals, when the ligands are going to approach in an octahedral field, what do we observe is the 3d orbitals, that is dxy, dyz and dxz. dxz are undergoing less repulsions. They are undergoing less repulsions. So they are going to have a lower energy, and these 3 orbitals are called as T2g. They are called as T2g. While the 2 set of d orbitals, that is dz square and dx square minus y square, which are collectively called as Ez, are going to experience a greater repulsion. Because they are going to experience a greater repulsions, they are going to have a higher energy, and they are called as Eg. And this difference in energy in an octahedral symmetry is represented as delta O or delta O. This stands for the splitting energy in octahedral field, and that is usually equal to 10 dq, and 10 dq actually represents 10 times of differential quantum. The electrons in the d orbital of the central metal ion and those in the ligand. The electrons in the d orbitals on the central metal ion and those in the ligand repel each other due to the repulsion between the like charges. They are going to repel each other because they have similar charges, and so because they are going to have the electrons present in them, so because of the like charges they are going to repel. The d electrons closer to the ligands will have higher energy. The d electrons closer to the ligand will have higher energy than those which are going to be farther away, and this results in the splitting up of d orbitals, and the d orbitals splitting in energy, that is there is going to be energy difference of 10 dq. The size of the gap delta between the 2 or more set of orbitals depend on several factors. This is going to depend on several factors, and they are going to be the ligand and the geometry of the complex. Some ligands, when they are going to approach, they are going to produce a small delta value, while others are going to produce a large splitting. Some ligands are going to produce a small splitting, while others are going to give a large splitting. And the reason for this can be explained using the ligand field theory. In fact, a spectroscopical series is a derived list of ligands ordered by the size of splitting. We are having a set of list of ligands which are going to be ordered, which are going to be arranged or ordered by the size of splitting delta, and they are going to predict whether the splitting is going to be small or large. So this is all about in octahedral symmetry. Thank you.